Let's see how to remotely operate, program, and test with Scopy a field programmable analog array. Just a few things. Is that in the Anadigm Designer 2, we've got a board already laid out from the company, but I've got the Scopy inputs hardwired, soldered in fact, so that IO cell 1, I have W1 and ground here. IO cell 2, I have the output channel 1 and channel 2 coming here. IO cell 3 has the waveform and ground in on these two pins, and IO4 has 2 plus and 2 minus there. You'll see when we get in that. To do the QIF, it's probably easier to download this Scopy ini file, and then when you start Scopy, load that in. That way everything will be there. And then you can download and open this design. Which has 2 quadratic integrating fires, as we'll see. So I have a machine set up for remote access. I'm not really going to give it out in a video, but so everything on this machine is set up. I thought the first thing is to look at, we just hook the inputs to the input to the output, so we can make sure Scopy's working. So the Anadigm FPAA just remembers the last thing you did, no matter who did it. This is how you program it, and you should hear 2 ding dings, and then it's done. Then when you go to Scopy, we can make the sine wave 1 volt peak to peak with an offset at 5 kilohertz, and then square wave at 5 kilohertz. I'm already running it, and so there you go. If you don't give an offset to the sine wave, actually you probably need to give an offset to that square wave, because it's just hitting the rail. The Anadigm is a differential topology, so if I really want a clean bottom, if you will, probably have to raise that a bit. Or not. Maybe I did it wrong. Okay, so now it's, that's kind of like the differential output, where 0 would be the minus voltage, and +4 would be like +2, and in the middle would be considered ground. It's easier to see with the sine wave if you do it incorrectly, because it just starts to clip. So let me just take away the offset on the sine wave. And now you can see this, and it's just starting to clip. If you do it more and more severely, you'll see it start to clip. Anyway, so now that's that, and you can easily do a filter, right, where this filter, it's 10 kilohertz bandwidth, gain of 1, quality factor 0.707, and it's an inverting filter, so then I just put it through another gain stage. Notice I have the input, and now in this case I can see the output, input as well, and then I just connect it to the output. So I just program it, come back here, and I'm just going to lower things. Actually, Actually, I'll just do this. Okay. So now the outputs are differential, and Scopy's waveform viewers or oscilloscopes are differential inputs. So anyway, you can see that, actually I should zoom in just a little bit because you can't see the overshoot. There we go. So you can actually see the overshoot because that's an underdamped system. Second order. Now here's two quadratic integrating fires. This one will go from -1 to 1. This one will go from 0.5 to 1. Unfortunately, they have an input, output, and I'm kind of out of channels, so you can't really see the inputs. I think if I add other Scopy to other kits, I can do that, but for right now, I'm limited to this. So let's go back. So you can see it's starting to work, but let's just put in some constant inputs so it makes a little more sense. So we'll put in a constant half a volt. Half a volt. Now, it's triggering off of channel 1, so they don't necessarily trigger very well with each other, but you can see it working. Not quite sure why I can't seem to get the period and frequency measurements on that. Yeah, I'm not quite sure what's going on. Anyway, but those are two quadratic integrating fires. One is in the bistable range and one is going from -1 to 1. That's pretty much it. You can, I'm just going to turn off channel 1, but if you can get a spiking rate, because we got a period 3.6 kilohertz. I can go to the signal generator, and if I recall, it needs 10 millivolts to spike. Yeah. Just give it a little more time. Okay. And it's a real device, so you can see it jumping around. It's not a crystal oscillator. I'm even thinking that bouncing around in the frequency, right, if I take the last 3 digits, maybe that'd be a random number generator. Anyway, so I could take the input at, I think it was 10 millivolts. There's my spiking frequency, right? 20. There's my spiking frequency. So I could easily get a spiking frequency map versus constant input B. Anyway, so this is all in my office. This is a real circuit. I forgot to take a picture of the setup. So I'll go back later. But I mean, it might look like it's all a simulation. But you can see that things are happening a lot faster than they would in a simulation. So I'm just going to get out, and so now I'll email you guys the everything you need to know, so you can do everything you need to remotely. Okay. So the thing is it will be doing that last circuit. Actually, yeah, it'll be doing that last circuit. And it's probably best just to leave it like that. I'm going to log out. Or it's better to log out this way. Sign out.